I wanted to do a few more examples on some of the things that can happen when you encounter these systems of equations. I'm still working the homogeneous system. We'll get to the non-homogeneous system in the next video, but for now let's continue solving homogeneous systems. So we'll work one like this. As usual, go and get the eigenvalues. So we'll have 4 minus lambda, 1, 0, 0, 4 minus lambda, 1, and then I have 0, 0, 4. Oops, minus lambda. And as I've mentioned in the past, you can expand along any row or column that you want. Here, if I go down the first column, I have 2 0 entries. That's going to make it so I only have one calculation to really do. I'll do 4 minus lambda, and remember, you cross out its row and column that it's in, and what's left is your submatrix that you're going to work. So I have 4 minus lambda, 1, 0, 4 minus lambda. And then if I were to continue my expansion, I would have 0 times something, and then I would have plus 0 times something if I kept going down this particular column. You might want to retry this problem and go along the last row perhaps just to see, but these are just going to zero out, so I don't need those. Let's just go ahead and get this particular computation done then. Remember, we're setting this all equal to 0. Alright, so I have 4 minus lambda. Now when I go down this way, I have 4 minus lambda squared. If I go the other way, I have minus 0. Set that equal to 0. And this just simplifies to 4 minus lambda, the quantity cubed, equals to 0. And so lambda is a repeated eigenvalue, 4, 4, and 4. So let's plug it in and see what an eigenvector looks like. So I'll put in my lambda equals 4 into this matrix. I will get 4 minus 4, 1, 0, 0, 4 minus 4, 1, 0, 0, 4 minus 4. And that equals 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0. So immediately you can see right now that y has to equal 0 and z has to equal 0. So, but x is not listed anywhere, so x can be anything. We call x is free. That's the terminology that's used. So when you create your eigenvector, I know that y and z has to be 0. X can be literally anything except 0. So probably the easiest choice for x is to allow it to equal 1. So I have one eigenvector. And so my solution right now, I have one solution because I did not get 3 eigenvectors out of the deal. So far then, my one solution is 1, 0, 0 e to the lambda for t. So there's 1. How do we construct the 2 other solutions? I mentioned last time that you can get a second solution. Here we'll call it P arrow, and it solves the following system. So in our case, let's plug in the things that we have. My A was, well, 4 minus lambda I here, the A minus 4I. We already had that matrix. 0, 0, 0. I had a 0 down the diagonal. I had 1s in only a couple of places. Yep, I made a mistake there. Now for the time being, I'll just call P sub 1, P sub 2, and P sub 3. And the K we found to be 1, 0, 0. So what we have then is when we do this multiplication, I take this first row and multiply it along the first column. That means is this 0 times P1, this 1 times P2, and then this 0 times P3. I end up with P2. For the second row, when I multiply it all along here, it's 0 times everything. It just zeroes out. And then finally, when I multiply this second row by this column vector, I'll get 0 times P1, 0 times P2. So I'll get 0, 0, P3. And then the last one gives me a 0. And we'll set that equal to 1, 0, 0. And we see that P2 equals 1. So then that tells me that the vector P is equal to 0. P1 was 0. P2 was 1. P3 is 0. So far, a second solution is afforded by this. So anyways, the second solution will look like the following. I'll have this time t e to the 4t, so that's like the repeated version, the one-dimensional repeated version. But then you have this new guy here, which is the one we just found, 0, 1, 0, e to the 4t. And then that's a second solution. I need a third one now. So to get that, we do something similar to what I did up here, where I solve this system and put the p here and the k on the other side. I can get another solution. Another solution will involve q, and I will solve the following. And you keep working it that way. If I had a bigger system, my next one would be an R that I would slide out here and a Q that I would put over on that side. Let me go ahead and throw in my matrix. I have 0, 1, 0, 0, 0, 1. This time let me call my Q, Q1, Q2, and my P, of course, was 0, 1, 0. Let's go ahead and multiply it through. I do this first row against this column up. Q has 3 entries. This first row against this column, I'll get a Q2. When I do the next row, I'll get a Q3. And in the last row, I'll zero it out. You probably could have guessed this. Q3 is equal to 1, and so my vector Q is 0, 0, 1. A third solution then is given by this. I have my K, or, well, let me go ahead and write this. T squared over 2 factorial times e to the lambda t plus p t e to the lambda t plus q e to the lambda t. So let me throw in my numbers then. My k is 1, 0, 0. T squared over 2 factorial e to the 4t plus 0, 1, 0, t e to the 4t, and finally plus 0, 0, 1, e to the 4t. So our entire solution then, if I want to write out the whole shebang in one line, it'd be very hard actually, but let's try it. Let's go back to my x1, which was k, and put a c1 out here, e to the 4t, plus, and then we have c2. Here I had 1, 0, 0, te to the 4t, plus 0, 1, 0, e to the 4t, plus c3, 1, 0, 0, times t squared over 2 factorial e to the 4t, plus then the vector p, 0, 1, 0, t e to the 4t, and then finally q comes into play, 0, 0, 1, e to the 4t. And there is our entire solution. Now let me pick one here that has non-real solutions for our eigenvalues. Here I have 1, negative 8, 1, negative 3, x arrow, and as usual let's go ahead and find our eigenvalues. So I have 1 minus lambda, negative 8, 1, negative 3 minus lambda, and we're setting that equal to 0. You go ahead and do my cross multiplying, and I'll get 1 minus lambda times negative 3 minus lambda. I go the other way, I'll get plus 8 equals 0. You go ahead and multiply this out. I'll get negative 3. Negative 1 lambda plus 3 lambda will give me 2 lambda. And I'll get plus lambda squared plus 8 equal to 0. If I organize a little bit, lambda squared plus 2 lambda plus 5 equals 0. And so I use the quadratic formula. Lambda equals negative 2 plus and minus the square root of 2 squared minus 4 times 1 times 5. All of that divided by 2 times 1. That equals negative 2 plus and minus. Here I have 4 minus 20, so I have the square root of negative 16 all over 2. That gives me negative 2 plus and minus 4i all over 2. And when I simplify that, then I get negative 1 plus and minus 2i. So let's go ahead and work. So I do at least have 2 different lambdas, so they'll be able to provide us with all of the solutions. Let's start with lambda 1 equals negative 1 plus 2i. And let's throw it in the matrix. I have 1 minus negative 1 plus 2i, negative 8, 1, negative 3 minus negative 1 plus 2i. And let's simplify here. I get 1 minus negative 1 will give me 2. I'll have 2 minus 2i, negative 8. And then I'll have a 1. And then I'll have 3 plus 1 will be negative 2 minus 2i. Now, in case you don't believe me, I'm going to go through this computation, but it turns out the first row is a multiple of the second row and vice versa. If I were to try to wipe out the first row, this 1 is very nice to use for that. What I might do is do negative 2 plus 2i times the second row plus the first row. So the way I've written it then, I'll have -2 plus 2i. I'll zero that out easily. It's what's gonna happen on the other one when I do this? Well, I'll have to multiply this stuff by -2 plus 2i. So -2 plus 2i times -2 minus 2i. You may know what's going to happen because you see that I'm multiplying a complex number by its conjugate. That is, you change the I part from positive to negative and you have a conjugate. Well, let's multiply it out nonetheless. -2 times -2 will give me 4. And then when I take -2 times -2i, I'll get a plus 4i. But when I do the other part of FOIL here, I'll get a minus 4i, and those will cancel. Finally, I'll be left with minus 4i squared. And you know that I squared equals -1, so I have 4 plus 4 equals 8. So this stuff, when I multiply it by this, I'll have an 8 here, and then when I add it to the first row, I'll zero that out. So you can see what's going on here. So for me at least, let's go ahead and get a vector associated with this thing. Here I have x minus 2 minus 2i. Probably if I put a negative in front of it like that. And then I can add it to the other side. And there's not a lot of easiness that goes on here. If y is equal to 1, for example, x equals 2 plus 2i. That there, I shouldn't have put an equal sign just yet. That guy right there is my first eigenvector. Now let me work the second one. This one, let me see, the first one was -1 plus 2i. So this one is -1 minus 2i. And then what I'm going to work is 1 minus -1 minus 2i, my -8, my 1, -3 minus -1 minus 2i, 0, 0. Let's simplify a little bit. As before, I'll get 1 minus -1 will give me a 2, and then -2i will be plus 2i. The -8 is unaffected. Down here I'll get 1, and then I'll get 3 minus -1 will be -2 plus 2i. So it's similar to what happened before, but not exactly. I don't think I need to convince you that I could wipe out the first row just like I did before. I'll cut right to the chase. X plus -2 plus 2i. Y equals 0. I'll take y to the other side and I'll get 2 minus 2i. Y equals 0. So for my second vector, I'm going to get, if I let y equal, say, 1, then x will be 2 minus 2i. So what do we have then for my solutions? My first solution, x1, I had 2 plus 2i, 1. That's attached to e to the -1 plus 2i t. And the second one equals 2 minus 2i, 1, e to the -1 minus 2i t. So those are my two solutions. Now I'm going to make these more appropriate for our types of answers. For example, all these i's in here are very complicated. And what I'm going to do is I'm going to go the long way around at first, show you how we get the answers, and then I'll show you how to cut through all the red tape and get the answer much quicker. So let's take a look at my answers. My whole answer looks like this. X equals C1 2 plus 2i, 1, times e to the -1 minus 2i, plus C2, 2 minus 2i, 1, e to the negative 1 minus 2i, t. Now one thing I'm going to do is you'll notice that I can break this up here. The e to the negative 1 plus the 2i. So if I have e to the negative 1 plus 2i times t, I can write that as e to the negative t plus 2it, or e to the negative t times e to the I times 2t, negative t. I'm going to factor an e to the negative t out of everything. But that will leave me with a bunch of stuff in here. C1, I'll put my 2 plus 2i, 1. That leaves me with an e to the I times 2t, plus C2, 2 minus 2i, 1, e to the, I guess you could say I times negative 2t. Do I want to do that? Yeah, that's fine. Negative 2t. And you've seen this before. I'll bring out my e to the negative t. I'll keep bringing it down. I get 2 plus 2i, 1. I'm going to use what is known as de Moivre's theorem, where I can convert this to cosine and sine. So I get cosine of 2t plus I sine of 2t. And then for the second piece, C2, 2 minus 2i, 1, e up, cosine of 2t. Remember, because cosine is an even function, it can squash that negative. Whereas sine, you'll have to bring the negative to the front, because it's an odd function. And now I'm ready to do a bunch of simplifying. This, remember, since t is, you plug in t and you'll get a number out here. You just can multiply it to each of the two parts. So I'll have e to the negative t. I'll have here this 2 plus 2i. Well, I don't think it hurts anything. I'll leave it as 2 plus 2i times cosine 2t plus I sine of 2t. But now the 1 is no big deal. I'll just get cosine of 2t, I sine of 2t. And that takes care of the first vector. I'll multiply this out in a second. I'm missing a C1 here. Let me go ahead and put it here, C1. The C1, let me put it after it this time, plus C2. I'll have 2 minus 2i times cosine of 2t minus I sine of 2t. And then below I'll have cosine of 2t minus I sine of 2t. All right, let's go ahead and multiply this out. If I FOIL it out, I'll get 2 cosine of 2t. I'm going to do the parts that I know come out to be real first. You can check this out later. 2 times cosine of 2t is no big deal. I get 2 cosine of 2t. But then, when I do the 2i times the I sine of 2t, I'll get negative 2 minus 2 sine of 2t. And then for the parts that involve I, I'll get 2i cosine of 2t, and then I'll get a 2i sine of 2t. So I get plus I. Of course, down here is nothing. All that is attached to C1, then to C2. Let's see what happens here. I'll do the real parts as I did before. 2 cosine of 2t. Then when I do the 2i times the I, 2i times I will be -1. Notice this negative and this negative both cancel. So I'll have 2 cosine of 2t minus 2 sine of 2t. And then for the imaginary part, I'll first have negative 2i cosine of 2t, and then I'll have negative 2i sine of 2t. So what I could have done here was left that as a negative and have 2 cosine of 2t plus I sine of 2t. What I'm going to do is break each of these vectors up into real and imaginary parts. So I get my e to the negative t. Let's see what we have here. I'll be able to break this vector up into 2 pieces. 2 cosine of 2t minus 2 sine of 2t. And then cosine of 2t. That was attached to C1. So I took all the real parts, this portion right here, and then this portion, just the cosine 2t, plus, and then I'll have an I. Now I have 2 cosine of 2t plus 2 sine of 2t. And in the bottom part, I'll have sine of 2t. And that's attached also to C1. I'll do the same for the second vector. Here the real parts are 2t minus 2 sine of t, 2 cosine of 2t minus 2 sine of 2t, 2 cosine of 2t plus 2 sine of 2t, and I'll have sine of 2t. An interesting thing to point out here, notice that I have a plus I and then I have a minus I. Well, that tells you, and the real portions here are the same for both of these vectors. It's the imaginary part that is different. In fact, one is the conjugate of the other one. But anyways, let me continue. I'm going to notice that these are 2 of the same thing, so I'm going to add them together. And I'll have the C1 plus the C2 times 2 cosine of 2t minus 2 sine of 2t all over cosine of 2t. Then on the other hand here, I have IC1 minus IC2. And then I can write it as multiplied to the same vector. 2 cosine of 2t plus 2 sine of 2t all over sine of 2t. And as we've done in the past, I will rename my constants as needed, and I can write my answer anew as e to the negative t. I'm going to call this C1, maybe a big C1, just to differentiate, but I don't need to. And I'll call this a big fat C2. And there we have it. Similar, but not exact, to what we had when we were doing the one variable case. This leads me to complex eigenvalues. In this course, we're never going to work with matrices that have non-real entries. So whenever we're calculating our lambdas and things like that, the polynomials that we'll have will always have real coefficients. So when lambda 1 equals alpha plus beta I, we are guaranteed an eigenvalue lambda 2 will equal alpha minus beta I. So this happens automatically. I don't even have to, well, you're going to have it anyways, but there's more to it than just this. The way the solution can be written is very nice as well. Use the notation the following. If I say a lambda with a bar over it, let's say it was lambda 1, that is alpha plus beta I with a bar over it, simply equals alpha minus beta I. This bar is the conjugate. Bar indicates we're going to take the conjugate. So when you get your answer, it's going to look like this. You'll have a C1, K1, e to the lambda 1 of t, but your second answer will automatically take the following format. I'll get a K2, but it'll actually be K1 with an arrow, but I'll put a line over top of it. And then I will get e to the lambda 1 with a thing over top of it, t. So this is guaranteed to happen. I don't have to search around for second eigenvector. It's automatic. All I got to do is take the conjugate of each entry in the vector. So let's do this last example. So example 6. I want to do a do-over. We found K1 was equal to 2 plus 2i, 1. That means my second K2, the second eigenvector, is guaranteed all I do is go through the entries and take their conjugates. So you get 2 minus 2i, 1, because this is like plus 0i. And then my answer, let's see what it looks like here. I get C1, 2 plus 2i, 1, e. So the first lambda was, what was it, negative 1? Negative 1 plus 2i times t. Then automatically the second one is guaranteed to be 2 minus 2i, 1. And you'll also take the conjugate up here. You get e to the negative 1 minus 2i t. These are guaranteed. In addition, let me continue my equals. C1, 2 plus 2i. I'm going to do like I did before. And you might recall that I factored out an e to the negative t. I'll put it out here, e to the negative t. That left me with e to the 2it. And that was cosine of 2t plus I sine of 2t. Second piece, I should probably put down here the same thing, cosine 2t plus I sine of 2t, C2. And I'm going to stop right there. Check this out. If I just multiply out the first vector, e to the negative t, C1. And let's do the real and imaginary like I had before. So I have 2 cosine of 2t, and then I had minus 2 sine 2 cosine 2t minus 2 sine of 2t. Then what I'm going to do is down here, just take the real part. And it's attached to e to the negative t. Now this will, by virtue of that, also be attached. I'm going to break the I stuff off of there. So I have e to the negative t, c1i, and that will give me, let's do the I portion, so I'll have 2 sine of 2t plus 2 cosine of 2t times I. And the bottom part will just be sine of 2t. Now I can simply write my answer in the following format. I'll just call this stuff C2. And let's compare it to my answer. Let's go back to the solution all before I start talking about these things. Here it was. 2 cosine of 2t minus 2 sine of 2t over cosine of 2t. There it is right there. And the other part, in case you didn't see it, was exactly this stuff. So what happens is, I only need to compute one eigenvector. I don't even need the second eigenvector because we already know its structure and everything, and we already know what all these computations are going to lead us to. So it's easy. Just use one eigenvector and you'll get both solutions. I want to do one last, little more complicated example so that you can see how the previous thing that I did relates to this one, which will need 3 independent solutions. So let's go ahead and find our eigenvalues as normal. I'll have 4 minus lambda, 0, 1, 0, 6 minus lambda, 0, negative 4, 0, 4 minus lambda. That's equal to 0. Now, if I look through my rows and columns, the best row, or the row that has the most zeros, is the middle row. So I'll have 6 minus lambda times what's left over. I'll have 4 minus lambda, 1, negative 4, 4 minus lambda. The only thing I got to figure out is whether it's positive or negative. The way you move here is in the top left corner, this starts off with a positive sign attached to it. And then as you go on, you have a negative and then a positive. But anytime you go and pivot from one spot to the one adjacent to it, you change the sign. So this starts out as positive. It has a +1 in front of it. When I go down to the 0, it technically has a negative. Now if I move to the right, it becomes positive again. So here I'm going to get 4 minus lambda squared plus 4. That's equal to 0. Well, 1 is very simple. I'll get lambda, I'll call it lambda 1 equals 6, and then I have to find the other lambda values here. So I have to solve 4 minus lambda squared plus 4 equals 0. I'm not going to multiply it out. Instead, I'm going to show you a slightly different way that can save you some time. I have 4 minus lambda squared equals negative 4. So if I take the square root, I'll get 4 minus lambda equals plus and minus 2i. And then I can subtract 4. And then multiply through by negative 1. So I get my lambda equals 4 plus and minus 2i. And you see a 4 plus 2i and its conjugate, 4 minus 2i, is there. Let's start with lambda 1 equals 6. this will be my lambdas 2 and 3 over here. Let's start with lambda 1 equals 6 and see what we get. Here we're going to get 4 minus 6, 0, 1, 0, 6 minus 6, 0, and then negative 4, 0, 4 minus 6, and we're setting that equal to 0. So I end up with negative 2, 0, 1. The second row is simple, 0, 0, 0. The third row will get negative 4, 0, negative 2. And once again, I'm forgetting where I need to be. I hope it's easy to see that I can take the first row, multiply it by negative 2, and wipe out the third row, and I would be left with negative 2, 0, 1, 0. Everything else zeroes out. Now what we have is we have 2x equals z. However, y is free. So you can let y be anything. So when I'm going to set up my vector like this, it's almost always the easiest to allow this thing to equal 1. And then here, you could allow z to equal 1 and you would get 2, and for x and z would be 1. But even easier than that, since by putting this here, I don't have a 0 vector, I could allow z to be 0, which forces x to be 0. That's a very simple eigenvector. And that was attached to the eigenvalue of 6. So one of my answers looks like this. 0, 1, 0, e to the 6t. Now we have the other two to deal with. Lambda 2 was 4 plus 2i and 4 minus 2i. Let's go ahead and throw those in. Just the one. I don't need more than one. Here we had 4 minus 4 plus 2i, 0, 1, 0, 6 minus 4 plus 2i, 0, negative 4, 0, 4 minus 4 plus 2i. So let's see what happens here. I get negative 2i, 0, 1, 0, and then I'll get 2 minus 2i, 0, and then finally I'll get 0, 0, negative 2i. Now it may be a little cumbersome, but check this out. Right here it says that 2 minus 2i times y equals 0. Well, I don't know about you, but that corn forces y to equal 0. Same down here, negative 2i, z equals 0, so z equals 0. Alright, now that I fix this right here tells me that 4x minus 2iz equals 0. Notice I get the same thing here. If I multiply the first vector by negative 2i, or positive 2i, I'll be able to cancel the 4 and the 2 and I'll be able to wipe that out. All I'll be left with then is either this row or this row. I guess it really doesn't matter. Maybe I'll choose the first row because it's a little bit easier in my mind, just a little bit. easier, and let me grab that one instead. So we have negative 2ix plus z equals a 0, so z equals 2I. And then, let's see, and I already know y is equal to 0, so let me put that in. It might be easiest to allow 2ix. Maybe allow x to equal negative I. If you do that, then you'll have 2I times negative I, which will be negative 2I squared, which will be positive 2. So then we have I 0, 2, negative I 0, 2, and this was attached to what? This was attached to lambda equals 4 plus 2I. So I'll have I'll put an e to the 4t in front of it, but behind it I'll put an e to the 2it. So I don't want to forget that. E to the 4t. And let's go ahead and do the usual thing here. I'm going to have negative I 0, 2 times cosine of 2t plus I sine of 2t. And that'll equal e to the 4t. When I multiply it through, this I through, it'll give me negative cosine 2i, but then here, a negative I times I gives me a positive 1. So it's sine of 2t minus I cosine of 2t. The 0 will stay 0. And then the third piece will be 2 cosine of 2t plus 2I sine of 2t. This equals e to the 4t times sine of 2t is 0, 2 cosine of 2t plus I times negative cosine of 2t, 0, 2 sine of 2t. And now I have all my solutions. Remember the first one. Let me see the one that was attached to 6. The eigenvalue 6 was 0, 1, 0. E to the 6t. And now these here give me my second two solutions. So I can have my e to the 4t out front should I desire. And I'll have a c2 sine of 2t, 0, 2 cosine of 2t, plus a c3 negative cosine of 2t, 0, 2 sine of 2t. So all you have to do is expand out the one eigenvalue and you'll be able to get both solutions.